Okay, welcome you all to the Brazilian Algebraic Geometry Seminar. So today we're going to have Cecília Salgado from the Federal University of Rio de Janeiro, UFRJ, and she's going to talk on the Mordell-Weil rank jumps and the Hilbert property. So please, Cecília.
Thank you very much, Eduardo, for inviting me. Okay, so let's start. First thing, so all this that I'm gonna talk about, especially the new things, actually, they are joint work with Dan Loughran from the UK, and it's been out for a while now. So let me start giving you what's gonna happen through the next 40 minutes or 50. So I'm gonna tell you the plan. I'm gonna start by very slowly giving you the main definitions that are gonna come up. I will go over one example or two for each of them, so that you can feel a little bit that you know them a little. And then I will tell you what do we want to do and what do we know for that. Then I want to go over the idea that we had to deal with this thing that we want to do, that I will say soon, to finally finish by telling you what can we do more about this problem, okay? So let's start with the main definition of this talk, and that's that of one elliptic surface. So this is a very basic, general, let's say, definition. I'm going to take a smooth projective surface, and I'm going to say that it's an elliptic surface if I have a flat morphism from that surface to some curve B, such that a few things hold. Namely, the first thing that I want is that the fibers, they are smooth curves of genus 1. So when I say for almost all, I mean for all but finitely many of them, okay? I'm going to suppose that I have a section for this fibration. So this is not standard for the surfaces to suppose that, but for the things we want to speak of, namely the rank, we have to suppose that we have sections. And I suppose, moreover, but that's just to make it simple, that this, so that pi is a minimal, fibration. So what does it mean? This doesn't mean that the surface is so the surface can have -1 curves inside of it. It's not minimal necessarily, but I cannot have them contained in the fibers of pi. So that's what I mean by being, minimal. Pi is minimal, not the surface S. I don't suppose that the surface is minimal. So a picture is worth more than any word that I could tell you. So let's look at what it is. So I have this black surface here. B is my base curve. Actually, for simplicity and for this whole talk, you can suppose that B is just the line, projective line, P1. Okay? So what you see here is my surface in black. Above a point of my line B, I have my fiber, which is normally like a smooth curve. For some points, I have something singular, which I drew here. I drew the generic point in blue and the generic fiber lying just above it, okay? And something that is very nice from these surfaces is actually that you get for free a way to write them down. So I wrote this here. It's an equation which is called the short-Weierstrass, equation. To write it in that way, I'm supposing that the field is not of characteristic 2 nor 3, okay? And very soon I'm gonna suppose actually that K is a number field. Yeah, so it's a number field. It's a finite extension of Q, the rational numbers. I said that I have a section. Let me draw it. It's in green. Sections correspond to points, so they are in one-to-one correspondence with KB points in my generic fiber. So I drew this point here. So for the sections, I have points in the fiber above the generic point. And I will say that the group of sections, so we have that the group of sections is actually the group of rational points in the generic fiber, where when I say rational, I mean KB points in the generic fiber, okay? I'm going to draw one more curve because it's going to come on very soon. It's going to come up very soon. And that's in this curve that I drew here. As you see, it's meeting the fibers in more than one point. But still, it's not a fiber because it meets the fibers, right? So this is what we call multisection. Okay, here, since it meets in 2 points, it's a bisection. And you're going to see more of them very soon in the talk. So let's move on. And I mean, this is something that is very, I mean, that is something that I think we should all say when we are working on something. Why should one care about it? And it turns out that these surfaces, they are lying in many, many places, more than you can imagine. So here are just a few of them. There are many more reasons to study these surfaces, but let me give you a few. So if you like, say, geometry, you might like the fact that the Shioda-Tate formula tells you that you can recover the Néron-Silverman group of the surface once you know the Mordell-Weil group, so the group of sections of pi. And T would be some lattice, which is given by information on the bed fibers of this fibration together with the zero section and a smooth fiber. So that's what T is actually encoding. So these are all very nice. They're all lattice. It's just that it's very hard to know something from them. So if you know of one, you know something from the other. And that's something which I find very useful. If you like number theory, they have been used in many, here I just put two papers that use them, but they have been used much more to show problems like to deal with the risk density, potential density of K points in your surface when K can be a number field. So they have been appearing. So in Bogomolov-Chinkel, they use it to deal with K3 surfaces. And in my work with Van Lauk, we use it to deal with Del Peso surfaces of degree 1. And many other people use them to deal with potential density. For example, Sinerton-Dyer, if I'm not mistaken, used elliptic surfaces, more precisely, more than one elliptic surface in K3 surfaces to say something about them. And so let me tell you a little more why you should care. More recently, in 2015, if I'm not mistaken, they were used to prove K-unirationality of conic bundle surfaces of degree 1. This is Kolar-Mella came up with a very nice proof. So these conic bundles of degree 1, they carry this structure of like a genus 1 fibration, and it has a section there, which lies there naturally, and they use it to prove that these conic bundle surfaces are unirational over any field, any perfect field, or actually any field. They were used much before in the 80s and 90s to provide dense sphere packings. The densest ones, I'm not gonna tell you in which dimensions, but they are still holding the record of the densest, sphere packings by using the Mordell-Weil group of some surfaces, which are, well, actually not so complicated, but this appears in two works which are not related. First Shioda and later Noah, they showed that you have very dense sphere packings, okay? In at least 3 different dimensions, which are quite high, more than 60, but I'm sorry, I don't have them in my mind now. Even more recently, last year, I used them to construct good correcting codes, actually locally recoverable ones, with Tony Verily and with José-Philippe Valoch. And I think there's still a lot of things to come out of there. We use it very, very little of them, and I think we can do much more by using this nice, surfaces, like structure that lies inside of the surfaces. And in the around 2000 something, I think I was a PhD student, Noah and Elkis gave, so around 2008, the highest rank of an elliptic curve that we know over Q is at least 28. So he did that actually by looking at a K3 surface, okay, that had an elliptic fibration that had the highest rank possible for such, which is 18 over Q, but he managed to find fibers for which the rank was much, much larger, namely 28 at least. And this is still holding for more than 10 years now. So that's a few reasons to care, but I'm sure that many of you could give even more than me here. So before we move on, let me tell you what are the simplest surfaces that have such structure. So when I say simplest, it's because I'm not looking at a product. Say you could take an elliptic curve, E, take the product with some curve B, and of course you'd have the fibration to the B line such that above each point of B, you would have E, right? E. I'm not speaking about those now. There's not much about the ranks that we want to say about those. So let's construct the simplest one, which is not trivial in that sense. So that's a rational elliptic surface. And we can start with F and G to plane cubics. Okay, I suppose that F is a smooth curve. Just to don't get into trouble, I can construct actually sometimes with two bad curves if I want a specific fiber type to happen. But here, let's suppose that F and G are two smooth plane cubics, or at least one of them. Then, of course, we know that they meet in 9 points, counted with the multiplicities. They can meet in 1.9 times, actually. And so this gives you a map from the plane to the line that takes a point in P2 to F of that P and G of that point, right? So I have this map. And clearly, this map is not defined where? At the points that F and G meet, these 9 points. So what do we do to get a real morphism, something that is defined through all the points? I blow up these 9 points, and I blow up multiplicities, like really meaning that if a point is multiple, I will blow up the point and whatever lies above in this direction that they meet, right? And by that, I get a surface, which is birational to the plane, clearly. And it has this map, which is really morphism to P1. And the fibers, they're just combinations of F with G, right? So I take a TU in P1, and the fiber above TU is going to be TF plus UG equal to 0. So that's how you build your surface. You can say that it lies in P2 cross P1 if you want, if you're looking at the pairs, right, of points. And what is very nice, actually, is that over C or over any closed field, all rational elliptic surfaces are given by that. This is not true over Q, but over K bar, where K is a number field, if you fix some K bar, they're always gonna be like that, okay? So when I say geometrically rational, means that when I pass to K bar, it's gonna be this, the surface, and this is gonna come up soon. Geometrically rational, which means that when I pass to K bar, the closure is gonna be rational to the separable closure, to the whatever, yeah. So, so now let's talk about number fields finally. So what about the arithmetic of elliptic surfaces? And all I'm gonna tell you here is actually arithmetic of elliptic curves. So for some number field, the fibers, they are elliptic curves. And therefore we can use Mordell-Weil theorem that tells us that the group of K points in some given smooth fiber is an abelian group. So it has some free part, which has rank RT. So RT is going to follow us through this whole talk. So keep RT in your minds, plus some finite part, which here are denoted by tors T, the torsion part of this group. We are not going to care for it, so just forget about it. We are going to care about this free part, ZRT, okay? But it turns out that we have the generic fiber, which is an elliptic curve over a function field. And for the generic fiber, we have the same theorem, actually, which goes normally by the name Néron. And this says that the KB rational point, so the group of sections, recall that I said to you that I have this one-to-one map from sections to KB points that lie inside my generic fiber. This is also a commutative group. So it has some free part, Z to the R, where R is going to be the rank of this group, and some finite part, the torsion part of this group. And when I state these two theorems, so which is actually the same, right? It's very natural to wonder how these two quantities compare, RT, R. Are they related somehow? And it's so natural that I was not the first one who thought about it. It's been there for a long time, this question. And so let's talk a little bit about the history of this question and what do we know about it. I'm not going to give an extensive result. I'm not going to go over all the results. I'm going to briefly say what we need to use for this talk. So I'm sorry that I don't cover the whole literature here. Far from that, the literature is rich. And as I said, I'm going to just speak about what I'm going to need to use. So the natural question, I repeat it, just that we can keep it in our minds. And that's the question of this talk. We're going to speak about how RT and R relate. And we have two theorems. So Néron, which dates back to the 50s, and Silverman's, which dates back to the 80s. And they tell us actually that RT is at least R for all but finitely many T in BK, so in my base. And for Silverman here, when the basis is not P1, I actually need to make the assumption that the surface is not constant, okay? So if you would have the product of an elliptic curve with itself, okay, this is an elliptic surface, okay? This is two-dimensional, E cross E, these fibers over E, and actually, if I have things right in my mind now, you actually have that the generic rank of this thing is 2. I can produce a new section. And the rank of the fibers is always the rank of E. So if I choose E to have rank 1, this doesn't hold. So this Silverman, like specialization, his hypothesis is, I don't know if he puts that the J invariant is not constant, namely that means that it's not a trivial surface when I pass to one extension, to a finite extension, or if he excludes just trivial surfaces. But we know that RT is at least R. And Néron's theorem, just to be more precise, his theorem is much more general than that because he deals with higher dimensional varieties. So Néron deals with fibrations whose fibers are a billion varieties over a basis which can have higher dimension than 1. So it can be a higher dimensional basis. And what he shows is a quite strong result, which is that RT is at least R, far from a thin set. So thin is here in red to remind me and to remind you that I'm going to tell you what this is soon, but you have to be patient, okay? So wait a little bit and you will know what is thin. If you don't know, maybe you already know. And thin here is thin in the sense of Serre that I'm going to be speaking about. So if you heard about thin in the sense of Serre or in the sense of Hilbert, if you want, this is going to come back really soon, okay? Silverman actually is restricted to elliptic surfaces, so surfaces whose fibers are genus 1 curves and has a section, and he shows that this holds outside a set of bounded height. Okay, so for all but finitely many, but what is encoded is really the quality of this set, which is a set which is far from a set of bounded height. So another natural question, and this was already natural, so this was something that I dealt with in my thesis, which I finished a little more than 10 years ago, is could I say more about this really, could I say that the rank really goes up, jumps? So is it strictly larger than R, this RT? Can I say that it's RT plus 1 at least, RT plus 2? What can I say? So actually, we can say more. And again, I was not the first to think about it. Wonder why? Better bounds. So in 2000, a French mathematician, Billard, using results from number theory from several people, very like celebrated results. He actually from like really heights, actually, that's what I wanted to say, not number theory, but height theory, more restricted, more particular. He showed that if you suppose that the surface is Q rational, so what does this mean? This means that it's birational to P2, but over Q. And if you suppose, moreover, that the fibration is not becoming trivial after some finite extension of the base. So it has non-constant J map, J invariant. Then he actually showed that the rank jumps. So he showed that this set FR plus 1, which is the set for which the rank of the fibers is jumping, is an infinite set. He doesn't show much about the quality of the set. He does have a very beautiful numeric quantitative result, but he shows that the rank jumps so in an infinite set. And look that he is restricted to Q rational surfaces. And this is really because he is relying on the shoulders of people who did height theory, and many results for heights, especially in that moment, were known over Q. And they are, expect to hold, I would think so, even though I'm not an expert, over number fields. But this is because he was using results over Q, and that's what he could do with it. And then a few years later, I started my thesis, and my question was, can I do better than that? Can I replace Q by some number field? Can I do a better rank jump? Can I do something? I really swear to you, I tried to use heights. I got nowhere. I was just not capable. But I got to show something, and I got to replace Q, the rational numbers, by K, any number field. So from now on, K is always number field. And I got to get rid from rational, so which means birational to P2, to unirational. So I have this, this dominant rational map, right? From P2 to my surface. And then I did show that the set FR plus 1 is an infinite set. And again, I have no quality about this set. I just know that it's an infinite set. I can say a little bit more on the quality soon. And but I did a little more. Remember that I said, can I get a better rank jump? Can I do more than that? And actually, yes, you can. I actually show that if I have two conic bundle structures lying there, and this is very natural because you do have tons of surfaces that have more than one conic bundle structure. If you know the minimum model program for like perfect fields or for non-closed fields, you know that the minimal surfaces are Del Peso surfaces or conic bundle surfaces. And when conic bundle are really Del Peso, they do happen to be Del Peso when they have two conic bundle structures. So this is where these two possible minimal models over perfect fields or over any field. This is the work of Skovsky, and later there are papers by Fassman, Manning about these things. But when these two things meet, you have two conic bundle structures. So it's quite natural. It's nothing bizarre. Then I did show that the rank jumps of at least two. Who knows more? You can get jump if you suppose something like square free sieve and parity conjecture, all that, and then you go back to analytic number theory. And if you show that, if you do think that the sign of the functional equation varies, then you could get R plus 3 at least by using something like that. And I forgot to add here, but I do have a result for K3 surfaces as well, where I have FR plus 1 being an infinite set. But it's not what we want to talk about today. So as I've been hinting to you, the next natural question would be, well, I have no hope to get better rank jumps at this point. I don't want to do that now, but I would like to know a little bit more about the quality, because if you think about it, Néron, Silverman, they were telling about quality of the set. Néron said, well, this set, rank jumps far from a thin set. That's what he says, and this is a lot about quality. Joe Silverman was also speaking. He was looking at heights and saying far from a set which has bounded height, which is not a big deal in this setting, I will have that the rank is at least R. So it's natural to want now to inspect on the quality. And actually, we have expectations about the quality of these sets. And as I said, this comes from big conjectures, which are far from being proven. I mean, I do encourage everybody to think about big conjectures. I myself don't at the moment. But so here it is. What do we expect could happen? So our expectation on the quality of the set for which the rank jumps comes from Joe Silverman, who conjectured when he was showing this, specialization result, that the set for which the rank is either R or R+1 of the fibers is actually dense. There is some density. It has density 1 when I look at my fibers in like an order by its height. So I can put a height in my base, B. And when I take the limit, say, where the rank is R or R+1 of these T's up to some height M, and I divide from all the points in my bases that have height up to M, he does think that this limit is going to be 1. So it's dense in some sense. So what we have, if we would draw a line in what do we dream about? Density is to show that it's actually happening a lot. And I don't know how to do that. What I did know in my thesis, and what Billard also knew, and what probably many others have other ways of doing it, people who look at the Oppeso surfaces, especially of degree 1, they're faced with this vibration, so they probably have a lot of ideas, is that it's an infinite set. So if you want to show something like Zariski density, this is enough, right? It's an infinite set. You have many fibers, you have an infinite set of fibers that has rank at least 1, say. This gives you Zariski density. So this is great if you are happy with that. Also, this gives you unirationality. This gives you everything that you would dream of, but you still might want more in the direction of this conjecture, I'd say. Being very pretentious here, let's say that we want to be in the middle of that. So that's today's goal. We want to be in the middle. I've no clue of how to show density. I did show that it's an infinite set in a nice class of surfaces 10 years ago. So let's say, I'm very happy to say that 10 years later, someone came to me and asked me, can we do more? And first I said, well, I don't know. And then I met this guy once more, and that's how we started working on this. I was in Bonn in the MPI last year, and then Loughran came to my office to say hi. And I said, well, maybe I should say something to him, like, let me think of something to say. Oh, this question that you asked me last year, is the set thin for which the rank goes up? So this question came in a workshop where Marc Hindry and we collaborated in so really what we showed is that generalization of my result from my thesis, but for fibrations in a billion varieties. So the fibers, they are like a billion varieties. We showed something similar. We showed a little more actually, if it's a Jacobian fibration. And then was sitting there and he asks Marc, I was also sitting, but is this set thin for which the rank jumps? And Marc and I said, I don't know. I mean, it's an infinite set. And then I met again Dan, and we decided to think about it. And in one day, we had an idea of what this would be, what we would show, I mean, how, but of course, it took much longer than a day to conclude this project. I mean, we had a feeling, let's say, not an idea, but a feeling that this would work. And well, it seems that, like it did, and you're going to see it. So finally, thin sets. So let me tell you what is a thin set if you don't know yet what it is. Let's start slowly. So I have some variety V over some number field K, or some field K. Actually, for this slide, you can think K of being any field. And a subset of the K points of my variety is going to be called of type 1 if it's contained in a proper Zariski closed subset of V. Okay? And it's called of type 2. So this is type 1 and type 2. You find this definition, for example, in lectures in Mordell-Weil theorem by Serre. and it's called of type 2. I think you call C1 and C2 sometimes. If it's contained, so this is the important one for us, in the image of the K points of a dominant morphism of degree at least 2. So from some variety W that has the same dimension as V, you can think that. So T is lying on phi of WK, which lies inside of VK, of course. And a set is going to be called thin if it's contained in a finite union of sets of types 1 and 2. And so let's think a little bit. For me, first time that I learned this, I like this book a lot by Serre, these lectures on Mordell-Weil theorem, which is actually not only about Mordell-Weil, it's much more than that. And I do recommend it if you didn't look at it, because it's a very nice book just to browse. You learn a lot. And so for me, thin, when I learned it, I thought about it as Zariski density like 2.0, Zariski density turbo. It's much more than Zariski density, right? It's not only if it's not thin, sorry, I might be confusing you. So if a set is not thin, not only it is like a Zariski dense set, but it's more than that. And when we are working, for instance, with the line, of course, sets of type 1, they're finite, so we don't care much about them. So when you work with the line, the sets you care about are those of type 2. And remember, we are working with a basis B, which is of actually one-dimensional, so the same holds. But B for us is going to be the line, actually, as you saw the construction of like rational elliptic surfaces. The basis is P1. And we will say that the variety has the Hilbert property over the field if the K points is a set which is not thin. So not only it is Zariski dense, but it's more than that. And it's still wide open, for example, let's say, Colliot-Hélène, he did conjecture that unirational varieties over K would have the Hilbert property over K. And this is wide open. And actually, if you would have that, you would have an answer to the, to the inverse Galois problem, which is very much wide open, right? So a field is called Hilbertian if there is a variety that satisfies the Hilbert property over the field. So again, Hilbertian, if you want to think about it, if you never thought, think about it as the other extreme of being algebraically closed. Because, a C is not Hilbertian, right? And actually, let's see a few examples of these definitions that I just gave to you. And those are the last definitions of this talk. So some examples. Of course.
Cecilia, sorry, one question. And type 2, do you ask the variety to have the same dimension or?
Yes. I said, but I didn't write. Sorry, Vittorio. Yes.
Okay.
Yes. Thank you. Any more questions? I'm sorry, but I don't read the chat, right? I just see my screen. I don't know if you're crying. I don't know if you're laughing. I don't know if you went for a wine in the corner. I have no idea. So speak. If there is something which is not clear, I'm talking to you, right? Even though it sounds like I'm speaking to me, I would like you to understand. So please stop me if I say something false or that you think it's false at least, or if you don't understand. So back to the examples. First example, over number fields. So Pn satisfy the Hilbert property. So the projective spaces satisfy the Hilbert property. And so it means that number fields are Hilbertian fields. So this is Hilbert's irreducibility theorem is saying that Q is, is a field that satisfies the Hilbert property. P1 satisfies the Hilbert property. Pn satisfies the Hilbert property over Q. And this is behind Hilbert's theorem. Like a irreducibility theorem. So behind when you show that Sn is a Galois group of something, you specialize, right, from these polynomials in many variables. So this is all lying behind here. The reals are not Hilbertian. Actually, no local field is. To be Hilbertian, you would really need to have that K over K star to the power D is an infinite set for all these when you vary D. So no local field is Hilbertian. And so when you are big, powerful, close to being a closed field, and so on, you are not Hilbertian. And the set of squares in a number field is a thin set. So I gave one example of each thing. So the set of squares is a thin set, and this is clear, right? The set of any D power in a number field is a thin set. And they lie in the image of this degree 2 map, say from P1 to P1 or A1 to A1, whatever you like, if you prefer a fine. So finally, what did we do? So I said in 2011, we had this contribution for which the rank jumped in an infinite set. And Dan and I met about in 2019, and we discussed whether this set was thin or not. And we managed to show that if we suppose that the surface is geometrically rational, recall when I pass to K bar, so I am over, I didn't write here K number field, but K is a number field. The surface being geometrically rational means you fix an algebraic closure of your K bar, and over this is actually a blow up of the plane in the base locus of a pencil of cubics, right? And just one curiosity, if you didn't think about it, know that the vibration comes to a pencil of cubics. And I said that it's relatively minimal. So these vibrations, they are given by the anti-canonical linear system. So if you like to think about these things, they are given by minus Ks. So that's the vibration, okay? So this is a geometrically rational, which becomes rational when I pass to K bar. And I suppose, so there is a hypothesis here, that I have a bisection to the vibration, which has arithmetic genus 0. Then I managed to show that the set FR plus 1 is not thin, so that the rank jumps in a set which is not thin. And moreover, if I suppose that the vibration has at most one non-reduced fiber, recall that, well, my vibration can have singular fibers. I mean, if I want to talk about rank variation, probably this is the nice case to think about. I have singular fibers. It turns out that the Weierstrass model, the Weierstrass equation, when you write it, it might be singular. And these singularities correspond to singular fibers. But if the surface is singular, you have to blow up to get to some smooth model, to the Néron model. And that model, so you blow up ADE singularities, and you get curves that look like ADE, this kind of, it's a completed Dinking diagram, okay? And sometimes they are not reduced. So when you have a singularity of type D or of type E, you have non-reduced fibers. And if it has at most one of those, or I have a two-torsion section defined over my number field, then actually the rank jumps of 2 in a set which is not thin. So finally, some quality to the set where the rank jumps. And that's what we got. I will soon go back to the theorem. Let me maybe clarify or make a translation of some of the hypotheses. I explained to you what's geometrically rational. Bisection, remember one of like the first picture, the only picture I gave in this talk after Dan's face was that of a surface fibering over the line, and I draw this curve which met each fiber in 2 points. That's a bisection. So recalling a multisection is a curve lying in my surface that when I restrict pi to it and go to P1, it's a flat map, right? And the funny thing is that bisections on such surfaces, I'm gonna be able to show that they move. So actually, I could have replaced this as a conic bundle. But I wanted to pretend that I did something very nice, so I put bisection, but it's actually the same as one curve actually spans some linear system. So this hypothesis actually being rational over K bar means that it's a regular surface, right? So I have the H1 being 0, so I can use cohomology, and with being bisection means that it meets minus K in 2 points. So I can really work this out to show that the linear system spanned by this bisection has dimension actually at least 1, but it's actually 1. And having a torsion, I will come back soon. And the funny thing is that non-reduced fibers. So I told you I can have these fibers when I have D or E singularities, but being geometrically rational puts a constraint, puts really, it restricts how many non-reduced fibers I can have. And it turns out that I can have at most 2. And this is because the Euler number of such surfaces is 12. And so each bad fiber contributes to this number. And I can have at most 2 non-reduced fibers. And this happens in only one way. So what happened, the history of these theorems is that in 1 week, essentially, we showed the first one. Of course, later we had to prove a lemma because something was not clearly an integral scheme, but we knew how to show the first one. And the second one took months because of one class of surfaces. So it's actually one class because it has one-dimensional moduli, but it's essentially one surface, you're gonna see. But before I tell you about the proof, let's think about why couldn't I give an answer to Dan Loughran when he did come to us, to Marc and to me in 2018 in a workshop and asked whether this set was thin or not. So he really asked, is it thin, is it not thin? Because he also didn't know. Why couldn't I give a straight answer? Clearly it's not thin. Well, first of all, every example that I could think of that the rank was jumping was thin. Let's have a look at one celebrated example. So this is due to David Hollich. And you consider, for instance, so this is very celebrated in analytic number theory. Consider an elliptic curve, any elliptic curve over a number field with Mordell-Weil rank 1. And I produce a surface from it, which is given by the twist by the T. So T is in my line in P1, and for each T, I have the twist of E lying above the point T. And the generic rank of the surface is 0. This surface, for all squares, of course, that I can eat when T is a square, the Y can swallow it, right? And I go back to E. So for every square, the fiber has rank 1. So I have that FR plus 1 is clearly an infinite set because it contains the set of squares. But the set of squares is thin. So I don't know if the rank is jumping in a set which is thin or not. And actually, this surface fits in our theorem. This surface fits in the second, theorem. This set is actually not thin. FR plus 1 is not thin. It contains the square, but it contains much more. And we showed this. So we were very happy to see that one example, which was lying around for a while, fits in our theorem, in theorem 2, in the second one. So the ingredients of the proof, funny enough, they come from my thesis. They are very similar, and they come from much before me. I didn't come up with base changing, right? But this is what I used to make the rank jump in an infinite set. So I start with my surface, and I find some curve C that lies inside of my surface, okay? And I restrict the map pi to C to get the map phi. So the map phi is C to B, so it's pi restricted to C. And I base change. I take the fiber product, right, of S and C over B in this diagram. And I get an elliptic fibration on the fiber product for free. So let's suppose that the fiber product is smooth. So if the ramification locus of phi is far from the singular fibers, this is a smooth surface, but it doesn't matter if it's not. You can just blow up whatever problem. I get an elliptic fibration. Moreover, any section of S is giving me a section of SC, of pi C, but I have a new section, namely the inclusion of C in SC. So this is new. C inside of S was a multi-section, so it was not a section. It didn't contribute to the rank. I base changed by it, and I got a new surface which has as many sections as S, maybe more. So the rank of this new surface is at least R, but if the sigma C, the inclusion of C in the fiber-like product, is an independent section of the ones that came from pi, then of course that for the points that lie on C and map to B, I'm going to have that the fiber has rank at least R+1, because the surface as C is going to have rank at least R+1, and the points on B that come from C are just copies. I have just copies of the fibers, right? So I can just specialize to these points and get as many fibers as C has rational points that have rank R+1. And of course, all this only makes sense if the curve C has an infinite set of K points, because then I would get rank jump as I wanted on an infinite set, right? So this is marvelous if you can find, number one, a C which gives something which doesn't depend on the sections that came from pi, but moreover, a C that has an infinite set of K points. So namely, this means a C that has genus 0 and has 1 point, or that it's an elliptic like curve with positive rank. So those are things that are not lying for free on surfaces, right? At least not on any surface. So to make sure that the rank goes up, so to make sure, to be clear, that this C has an infinite set of points and that it gives a new section that doesn't depend, in my thesis, I showed that actually if C lies in a one-dimensional linear system or in a higher dimensional linear system, and it's not lying in some fiber, of course, that I don't want the linear system from the fibers, right? Then all but finitely many curves in this linear system could be used. Suffices one of them, but all but finitely many can be used to make the rank jump by this construction that I just showed you. So what do I have to do? I have to give hypotheses to make sure that the surface S contains a linear system of curves, so something that has dimension, right? It's not rigid, that has an infinite set of K points. Well, good candidate is K unirational surfaces. Actually, I didn't put this into my hypothesis, but you're going to see that the surfaces that I work with, they turn out to be K unirational. And we did use Collard, we did use Collard-Mella from 2015 to do that. So this is really, I couldn't have done this in 2011 or 2009, right? So let's use the hypothesis. So our theorem said that I have a geometrically rational surface with a bisection. So the fact that I have a bisection is crucial here, because for the fact that it's geometrically rational, so it's a regular surface, and with the bisection, as I explained to you before, I managed to show that it moves. And I managed, moreover, to show that I have actually P1s and not conics, not bizarre things that don't have points. But this requires an argument, and we show that we have P1s lying around my surface beautifully. And together with the fact that the surface has degree 0, so that K squared is equal to 0, I can use this using building up on results by Collard, Mella, and actually others. I can show that the surface is unirational. And at that point, I can use a curve on my linear system. I get everything that I need with my lemma from the previous slide to show that the rank jumps. Now, if you're following, if you're still there, I don't know, you might be wondering, the set is thin, right? Where is it jumping? The rank is jumping on the points that lie on the image of the CK points inside of BK, right? Phi CK. So this is a set of type 2. This is clearly thin. So one more reason to think when Dan asked it that this set is thin. But not everything is lost. Actually, I didn't think that it was thin. I think I never thought that it was thin. I mean, first of all, when he asked the question, I was not even sure what thin was very clearly. I had read it and I learned by doing this work. But our strategy is to consider all curves, because it turns out that my lemma says that, well, any curve, but finally many, will be useful to make the rank go up. So you have an infinite family of surfaces lying above your surface S for which the rank is larger. And well, you just have to specialize well. So you have an infinite union of sin sets, and that's not clearly sin or not sin, right? That was the problem we had. We had to deal with an infinite union of sin sets. So that's just to remember you that given, so what do I have to do to show that a set is sin? I have one more slide repeating this information, which is we are working with the line. I'm not going to care about the risky closed because I'm supposing that my curve has an infinite set of points, of k points. So we have to work with type 2. And so I have to take any, like a finite number of covers of the base B, which is P1. And I have to find a curve C on my linear system that has a k point that is not mapped to the same things of this cover. But what I'm going to do is that I take some cover. I don't know nothing about it. I cannot suppose anything about the cover, right? Other than it's finite. It has degree at least 2 is of curves. So I can suppose that the curves have genus 0 because if they would have genus 1, I would have 1, right? Because from the weak Mordell-Weil, we know that genus 1 curves don't satisfy the Hilbert property in general. So this is repeating what I just said in another slide. So we have to check that given any finite number of covers of the line, there is a point that lies on, I put T, this is a very unfortunate letter because I should have put N, right, for not sin. But I want to show that the set T is not sin. I have to show that there is a point that lies in T that does not come from the covers. And that's what we're going to do now. We're going to play with base change and covers. We have to get far from them. So the C prime lies on my linear system that I started with that came from the bisection. Okay. And what do I do? Well, if I take the fiber product, I have this diagram. And if the fiber product, I just saw that it's not very precise, the B is to the right, of C prime with Y over B is an integral curve. So it's something that is not just breaking in many. So it's just something, let's say, if it was non-reducer, this would be very bad. Or if it was 2 components, this would be very bad. So if it's an integral curve, then what happens is that the fiber product has genus at least 1. Well, C prime is P1. Remember, I said I can have P1 here. I'm on a unirational surface in the end, and I'm working with a bisection of genus 0. So this, I told you, satisfies the Hilbert property, which means that the K points in C prime do not all come from covers. So I have K points in C prime that don't come from the fiber product. Well, a point in C prime that doesn't come from the fiber product is a point in C prime that maps to some point in B that doesn't lie in the image of the yi's. That's exactly that I have to do. But so we did that. But how can I make sure that the fiber product is not splitting in many components or that it's not something bad? Okay, so that's the trouble that took us months, right? All this, clue, like this idea of what we had to do, we knew this in 2 days. And then all the showings of the things took much, much longer because this was not very clear. So what do I do? Well, we love curves because curves, function fields, we can work with whatever pleases us. And I know I have just 3 minutes. I will finish soon. So recall that I'm working with bisection. So I have a degree 2 map. That means that the function field is a quadratic extension. So if I have the ki, yi's, my finite extensions of B, then of course that if it's a finite number of function fields lying above KB, there is only finitely many quadratic subfields inside of these guys. Thus, what I have to do is to show that the set Kc prime over Kb of these function fields, when C prime is varying on my linear system, which is an infinite linear system, that this set has an infinite number of classes of quadratic extensions. So, and then I would be good if I show that. But how can I show that? How can I show that I have an infinite set of quadratic extensions? How can I show that they are not the same? So there are many ways to do that. One way that we came up with was that, well, if the ramification of these maps is varying with C prime, this is certainly true, right? The function fields are going to have different ramification, and therefore they cannot be the same. And this is happening when I have at most one non-reduced fiber, because ramification can only coincide for curves in the pencil when they hit non-reduced fibers. And well, this is just like intersection theory for schemes, for non-reduced and for reduced schemes. So this would be the case for the first theorem. The problem is when I have more than one. And remember, more than one, actually, they look very specific. There is one class, and this has this configuration of Kodaira fibers. And the Weierstrass, it's not a Weierstrass equation. I realized it, then I put just this kind of, it's an almost Weierstrass equation, is y squared equals to gt, where g is some polynomial of degree at most 2. So it could be, for example, t, which is the Holic thing that I showed you. And f is a separable polynomial of degree 3, making y squared equals f of x an elliptic curve. And therefore, this is a twist by g. So we have a bisection for free, which is every time that I take x0, when I fix x, this is a bisection. The problem is that you can vary x0, but they all ramify in the same point, namely in the zeros of g. So if it's t, the polynomial t, then it's ramifying in 0 and plus infinity. So how can I show that they are linearly disjoint? And this is the thing that we took a lot of time. And there is a secret about these surfaces that I didn't tell you. This is special surfaces, and this is, this includes the surface from the one example, the twist, right, from Hollish. So the first thing is that the function fields, they are looking like these quadratic extensions. I can write the set of k points in my surface. So if I would have only a finite number of classes of function fields, I would have that f of x takes up only finitely many values modulo squares, right? Because that's what determining these extensions. And I would be able to write the rational points of my surface as a finite union, but these sets are thin. The problem is that the surface is, has the Hilbert property. This was studied before by Colliot-Helenis and Suk. And this is a surface that has the Hilbert property. So Sk is not thin. So if there were finitely many classes of field, that lie above KB, this would be a thin set, and this is not true. So there are finitely many, so there is an infinite number, and this set is not thin, and we conclude the theorem 1. For rank jump twice, just to conclude, we can do, we can use curves in the same conic bundle when I have at most one non-reduced fiber. With two non-reduced fibers, we need a second conic bundle, and that's where the hypothesis to torsion comes in. And to conclude, I give you the directions. So the first one is, can you say more about the quality? I have no idea how to answer that one. Fibrations on a billion varieties. I have an idea of what has to be done, but I also, this is something I would like to think about. And I would say that you have to know a little bit more about the fibers of this abelian fibration. Otherwise, you cannot use the same method as I did, or you do something else. And my PhD student is now working on non-geometrically rational surfaces to show some similar results. Like he's working with K3s more specially. Renato G is working with that. So that's all I wanted to tell you today. Thank you.
Okay, thanks, Cecilia. Let's thank Cecilia. Okay, questions? Don't forget to turn on your microphone.
I stop presenting, okay?
Okay, well, yeah. I just have a simple question, I guess. I mean, you were assuming that you have a section on your elliptic fibration, right?
Yeah.
If you just double that section, can you move it to a bisection?
What do you mean double in the Mordell-Weil group or what?
Pick twice that. Pick twice that section and consider the linear system on that.
No, because this is the zero section, right?
Right.
I'm supposing this is the zero section, but there is an argument that, I mean, later, after seeing me speak about that, Colliot-Hélène came up with another way of showing a similar result, but he relies on weak approximation. He relies on other things which are stronger, and on complex multiplication on the fibers. But he came up with an argument which is maybe what you would like to do now, which is taking the diagonal. So he takes the fiber product of the surface with the surface. And then, well, okay, you have the two sections there, but so he takes the diagonal section. He takes something like that. And it's also very beautiful. It's very nice. It's just, yeah, a different way of doing that. And I would say it's parallel to our result, but we do a little more in the end because many surfaces don't, I mean, they are not known to have weak approximation. For example, del pesos of degree 1, they are not known to satisfy that. There's a big conjecture, I think, that from himself, actually. So if we would know that his conjectures are true, his work would be at least as strong as what we did, but we don't know.
Okay. Okay. Are there more questions? Okay, so let's thank Cecilia again.
Thank you.
Okay, thanks for showing up, and we'll see each other next week. Okay, take care.
Bye.